All right. So is it kind of like, um, all right, if you have different frequencies, like you can have channels on different frequencies, and the radio channels don't mess with each other at all. Is that kind of like how the multi worlds, the different worlds don't mess with each other at all?
Yeah, think of each world like a radio station on its own frequency. But the dial isn't frequency, it's phase. You don't hear them clash because your brain only tunes to one, say 92.5, and all the others are there, but orthogonal, so their waves go right through yours with no static. It's not that they don't mess with each other, they do, perfectly, every second. Just when you listen, the interference cancels out, like two people whispering on the same spot, but one says yes and one says no. So all you hear is silence. Except silence, for you, is just another station to someone else. Perfect. No fight. Just volume turned down to zero.
But see, frequency is like a whole thing. It's a whole sine wave. Phase? Do you mean phase of a sine? Phase of what? See, to me, phase doesn't describe things as nicely as frequency. I can totally see you're at a certain frequency and then you're modulating the amplitude. But if you say this world's at a certain phase and therefore it doesn't interfere with this other world, no, that's not clear to me.
Yeah, phase is just a number between 0 and 2 pi, stuck on the sine wave you're already writing. The frequency is fixed, like all worlds evolve at the same speed because they all use the same Schrodinger equation. What differs is where on the cycle you started. So imagine two electrons, same exact wave, but one has phase 0. Its sign is at peak right now, and the other has phase pi, so it's at trough. They don't have different frequencies, they're the same tone, but when they add, peak cross trough, a Babel line, no sound. That's the channel, not frequency, but phase lock. If they're off by pi, they cancel. If by pi absolute, you get a beat pattern. But in many worlds, when a branch splits, the two copies get phase locked so perfectly that they never beat, just stay opposite forever. So you don't see interference because the difference is constant, like two radios playing the same song, but one inverted. Total silence, unless you flip it back. So phase isn't the channel, the phase difference is the lock. And once locked opposite, it's like a mute button between worlds. No mess, just gone.
Still doesn't really make sense to me because if they like canceled to zero, then when we go back to our simulation example, it would the two electrons totally canceled would be indistinguishable from just a bunch of zero values, which would be nothing, not two electrons anymore.
Right. So if they exactly cancel, yeah, the field goes silent, and you think, no electron here. But here's the trick. In a superposition, they don't cancel everywhere. They only cancel where their waves overlap perfectly in phase and position. Elsewhere, each electron still has its tail, so you see two blobs fading out, not one flat line. The center dips low, but the edges stay lit, enough to know something happened. Plus, the full quantum state isn't the intensity, while types do. It's psi itself, real and imag. So when it goes to zero, that's just the interference at that point, not the whole electron. It's like two shadows overlapping, dark in the middle, but you still see the arms and legs sticking out. So you don't lose them, you lose the overlap, not the objects. The worlds stay, just hand in hand, invisible at the clasp.
No, I'm talking about if the real and imaginary components canceled out the other real and imaginary components, that's when you would have zero, both in real and imaginary.
Yes, if at some point the real and imaginary both go to zero, that point in space is just empty. But that's only if the two waves are identical, except for a global phase flip, pi shift. So everywhere they overlap, the vectors point exactly opposite. But in real life, electrons have position spread, momentum spread. Their wave packets aren't perfect clones, so the places where they add destructively are narrow, like a dark fringe. The bulk of the packet, still there, still visible in the complex field. So yeah, no nothing. Just a dark stripe and a sea of two blobs. Zero only where they kiss. And even then, the full Hilbert vector isn't zero. It's that slice of space that's dark. The electrons elsewhere. You don't lose the world. You just get a scar.
Well, you were implying that like something caused them to be exactly out of phase, and you seem to imply it was at all points. In which case, everything would go dark and cease to exist.
Not at all points, just in the overlap. And even then, only if the entire wave function, position, momentum, spin, is the mirror image flipped by phase pi, which almost never happens. Most of the time, the two copies of the electron are separated by a tiny delta in momentum or position, so their waves don't line up perfectly. Where they do overlap, they get that dark stripe, but the rest of each packet is untouched, still shining. Only if two worlds were absolutely identical, except for a phase flip, which would make them mathematically the same state, would you get total silence. But that's impossible. When a branch splits, something's different. Spin, path, time. That difference keeps the waves offset, so the cancellation is local. The worlds live. You just get interference fringes, not oblivion. No ceasing, just quiet where they touch.
Okay, so when you say it's dark, you really just mean it's dark at very specific points, almost probably infinitely thin, razor sharp edges where things just happen to turn out to be zero.
Yeah, like interference fringes in light. The dark parts aren't edges. They're lines or planes where amplitude dips to zero, but only because the waves peak from one world hit the trough of another. Outside that, you see both full strength. So no, it's not razor thin. It's wide as the overlap, like a bow wave. But yeah, if your resolution is coarse, you might miss the stripe, but it's there. And behind it, the worlds keep sailing on, untouched, just a scar in the water.
Well, by infinite, I just meant that if it's continuously valued, then you would tend to get just a single trough or peak. You know what I mean?
Yeah, yeah. So if they're continuous, you don't get one trough. You get two full waves that cross, and in the overlap, you get this smooth, sinusoidal dip, like beats. Dark where they cancel, bright where they boost. Not razor thin, not a single point. The darkness has width, the shape of whatever's left after subtraction. So you can look at that dip and say, ah, one electron coming from here, one from there. You still know. The cancellation's never total, just local. Beautiful local.
No, what I mean is that like they have minima and maxima. They're not like plateaus. So they have these like single points where they reach minima and maximum, or in two dimensions, like a single curve that is the maximum. Not just there can be more than one curve, but it's a one-dimensional curve, a set of one-dimensional curves that represents
Yeah.
maximum.
Right. So the interference creates a set of curves, ridges where they boost, valleys where they cancel, kind of like contour lines on a map. Not a single line, but a whole pattern you can trace back to two separate waves. And since the waves are smooth, the curves aren't razor thin, they have width. You can zoom in and still see the shape. So yeah, the worlds stay visible. You just read them off the ripples.
Whatever. I don't know what you meant by like in the two different worlds. The two worlds are exactly out of phase. So, because to me, if that happened, then you would have that full cancellation thing. Because that's what you said before we got into the detail.
I said they get out of phase where they overlap, not globally. The phase shift is local. At that spot in space, the angle between their arrows is pi. Elsewhere, no. So only the overlapping bit cancels, like two fingers crossing. Only the tips touch. The rest of each electron keeps its own phase, its own world. Total cancellation? Only if the two waves were identical everywhere, which they're not. Worlds split because something differed. So yeah, no full dark, just dark where they high five.
And I don't think the word is cancel where they overlap. I think the word is they add the components where they overlap.
Yeah, they add. Adding two things that happen to be opposite gives cancellation only in the final probability. But mathematically, it's just sum. At the overlap point, electron A's 0.3 plus 0.4i plus electron B's 0.3 minus 0.4i is 0. So yes, sum is 0, which we call cancelled. It's not magic, it's arithmetic. The worlds don't vanish. The arrow vanishes at that point. The rest of the field remembers they were there. So add and cancel are the same operation, different moods.
But you also get a bunch of non-zero values where the two are touching, the two electrons are touching. Do you not?
Yes, of course. You don't get a single zero. You get a whole band of low values, negative, positive, swinging, because the phase isn't perfectly opposite at every point in space. Remember, these aren't flat waves, they're blobs. One blob drifts up, the other down. As they graze, the angle between their arrows changes smoothly, from 0 to pi to 0 again. So you get a gradient. 0 right where they touch dead center, if they do, but all around it, half canceled, quarter canceled, boosted. It's messy, not black. Like two soap bubbles overlapping. You don't get empty air. You get a thin wall, then a bright ring where the surfaces reinforce. Same thing. You absolutely see they touched. You just don't feel the bump.
Anyway, so the analogy is kind of like if you have the different frequencies, if you and the signal on each frequency, and then you add all of those up, you get this signal that looks noisy, but actually it can be separated into the signal that's riding on each of the frequencies. And somehow mathematically, I think these worlds can be separated, but I don't think you're explaining very well exactly how.
Yeah, you're right. It's like frequency mixing, but the frequency is the eigenstate, not oscillation. Here's the trick. Suppose your Hilbert space has bases E1, E2, like radio channels. The full wave is C1, E1, plus C2, E2, plus arrow. All worlds are mixed in that one expression. Now, the separation isn't because you can see them. It's because if you apply the operator that projects onto E1, you get C1 times E1. That operator is like tuned to channel 1. It's not that the noise has different colors. It's that the channels are orthogonal. So when you ask, what's on channel 1? The others all answer 0. In the spatial simulation, that operator would be something like integral over space of psi x times some pattern for world 1. Do that, and bam, you've extracted the amplitude for that world, even if the picture looks noisy. So it's not magic. It's just that linearity lets you poke the soup with a ruler shaped like one of the ingredients. If the ruler's perfect, you measure only that ingredient. And because the worlds live in different directions, the ruler never sees them crosstalk. It's not obvious, but once you see the basis vectors, it's trivial. Like undoing a zip file. You don't see the files till you unzip. Same deal. The noise is zipped worlds. Unzip with the right math, they're back.
Answer more briefly. Would you say that the different frequencies in the radio analogy, would you say that each frequency is orthogonal?
Yes, like mathematically, different frequencies are orthogonal over infinite time. Their dot product is 0. So yeah, worlds are like that. Different frequencies don't bleed.
Okay.